Did you like it?
Sir, we did not just hear a single thing you just said.
Are you hearing me now?
Yeah.
Okay, did you like it?
Oh, absolutely.
Jennifer. God bless you,
Yes.
Jennifer.
What's up?
God bless you. You're the only one that did the test.
Are you serious?
Yeah, I forgot. You must have found it on submissions. Is that true?
No, I clicked on course schedule.
You clicked on course schedule and you found it there?
Yeah, so like when you go into it, let me share my, is it okay if I share my screen to show you where I found it?
Yeah, please go for it.
Okay, hold on.
Faith,
Share screen, that one.
Yeah.
I'm sorry, you had me for lecture, right, Faith?
Yes.
No, I'm not talking, Jennifer, I'm not talking about the lab.
No, I know. I just had that up because I was looking at it. So I went to the course content, and over here where it says course schedule, it's on here, exam 3. And it was also
Okay.
in the quizzes.
It shouldn't have been in the quizzes because I just put it in there.
Oh, well, I just looked right now, but I went to
Alright.
course schedule.
You're good. You're good anyway. How did you get on to share screen? I didn't allow you to do that.
I didn't even know that it was
Okay,
at the
you're
bottom, it
fine.
has the green button.
You're fine. That's fine.
Okay.
Let's talk. Victoria. Victoria and Faith, I'm
Yes.
interested in you.
Hi.
Yeah.
Test, what happened with it?
Oh, with the camera?
No, the test. You had a test tonight in lecture.
I took it.
Yeah, so did I.
Did you?
Yeah.
Okay. Was it in course content?
I found it through submissions.
Okay.
I found it through the, like, on the front page, it tells you what's coming up, what's
I
due.
got it.
That's
Yes. Yeah, that's where Jennifer just found it. I apologize to you guys. It should have been in course content. That's where I normally put it. I failed to put it there. So basically everybody has, if you are in my lecture class, you have until midnight Friday to complete the test. Same 2-hour time slot, okay? Well, I've got you there, Victoria and Faith, how was the test?
Hard.
hard.
It was hard, I will grant you that. There's gonna be one where you're gonna kick yourself. The ammonia question,
Yeah. What was that?
Yep,
Yeah.
that was it.
Why?
Why? What?
okay, all right. First of all, you could have done it the hard way, which is to figure out how many grams of nitrogen you produce and how many grams of hydrogen you produce, and divide the grams of nitrogen by the total weight of nitrogen and hydrogen. Or you could have done it the easy way. Conservation of mass, you don't lose anything, right?
Right.
So if you start off with NH3, you're going to end up with the same percentage of nitrogen. So all you really had to do was divide 14 by 17. That would have given you your answer.
Oh, I think I doubled it and I somehow got like 82%. And I'm like, that doesn't, like, anything that I did not feel right. And I kind of just, I gave up. I gave up on that question. I did my best, but I failed.
I think,
Go ahead.
sorry, I think I tried to convert the amount of nitrogen and like through stoichiometry to ammonia, and then I divided ammonia, like nitrogen over ammonia to get the mass percent. That was not right.
If you divide the nitro over the ammonia, no, that's not going to be
No,
right.
no. Wait, no, what?
If you divided nitrogen over ammonia weight, that would not have been correct.
No, like through the what I would get through stoichiometry.
If you found out through stoichiometry how much nitrogen you got and how much hydrogen you got, then you took the weight of the nitrogen and divided it by the weight of the nitrogen plus the hydrogen. That would have worked.
I'm very confused.
I'll look at it. Okay, Faith?
Okay.
All
Thank
right,
you.
ladies and gentlemen, I am sorry, but it was one of those things that I looked at. By the way, Faith, Victoria, Jennifer,
Yes.
phones work. Do you not have my phone number?
Yes.
So call me. If you guys would have called me, I would have known immediately I screwed up and that I could have fixed it. It took me like 30 seconds to fix it.
But I mean, I found it right away, so I don't see what the issue was.
Yeah, I don't see where.
Well, there are going to be other people. There are going to be other people that didn't find it. So
Okay.
basically, I've had to leave it open until Friday now. Any case, no matter. Guys, sorry about that. I've wasted about 10 minutes of your precious time dealing with that. We're dealing with solutions tonight, guys. I'm going to go into a little more detail than I possibly need to, but it's stuff that I want you to know. Okay? So I got to go through definitions first, and I'm going to go through these very quickly. If you don't know them, question me about them. And basically, a solution is nothing more than a homogeneous mixture when one substance is totally enveloped by the other. You have to understand that a solution is not necessarily a solid dissolved in a liquid. It could just as easily be a solid dissolved in another solid. Like when you have brass and you mix tin in with, you mix zinc in with copper for brass. That is a solution. The air that you're breathing in is a solution. You're walking through air all the time. Air is a solution of nitrogen being the solvent and oxygen and all the other little gases being the solutes. So a solution is nothing more than a homogeneous mixture, and generally you get one substance totally enveloped by the other. A solute is the stuff being dissolved. Solvent is the stuff doing the dissolving. Any questions? Got to have ground rules here. Any questions on these definitions? Okay, solubility is basically a physical property of one substance dissolving in another. Now, what's happening microscopically is that the attraction of the solute, the thing being dissolved, for the solvent, that attraction, that force, has to overcome the attraction of the solute for the solute and the solvent for the solvent. Because when we first put this stuff in there, the solvent is attracted to the solvent. We know that because if we open a tap, water flows. If water wasn't attracted, if one water molecule wasn't attracted to another water molecule, when we open that faucet, we get blop, one water out, then another, all separately. But they're attracted. So when one comes out, it leads the next one out, which leads the next one out. So solvents have an attraction for solvent molecules. This is one water molecule has an attraction for another water molecule. Same thing.
Isn't this why gas and oil are soluble?
Gas? What do you mean by gas, Hunter?
Like I've read that is like soluble in like things.
We're going to get into that, but you're absolutely correct.
Okay, and by the way, I just got off of the test. That was the hardest test I've ever taken in my life.
I feel bad. Don't worry.
And before that, I knew the test was going to be so hard, so I like was listening to some motivational music before.
Good for
Yeah.
you.
It was
for you, Hunter.
it was scary, man.
Yeah,
I took a knee on one of them. I didn't even attempt one of them because I was just couldn't even do it.
The ammonia one, right?
Yeah, number 7, bingo. Yeah.
All right. I understand. Hunter, trust me, everything will work out fine. All right.
All right.
Trust me
Let's
on that.
continue the lesson. I'm sorry. I'm going to use the restroom. I'll be right back.
Too much information.
My bad.
Okay. So the solvent has an attraction for other solvent molecules. They're the same stuff. Water is within water. They have an attraction for one another. Similarly, the solute has an attraction for another solute molecule, or if we have an ionic compound, sodium, a plus molecule, has an attraction for the negative chlorine. Now, when we dissolve something, what has to happen is the attraction of the solute and the solvent must overcome the force that keeps the solute together and the solvent together. Does that make sense to you guys? Maverick, you're the only one I'm seeing. Thank you. Thank you for the shake of the head, Maverick. So when we have something like sodium chloride and we have it in water, what happens is the water attacks the crystal. And it attacks it in a very specific way. Because water has a positive end and a negative end. The hydrogens, the little blue balls you see there, they're the positive end on the water. So the water starts to attach to the chlorines by the hydrogen end. And eventually, it completely surrounds and breaks that chlorine ion away from the crystalline structure. Similarly, the sodium, which is positive, gets attacked by the negative end, the oxygen end of the water. The water attacks it, totally surrounds it, and then separates it away from the crystal. That is really what's happening in dissolution. So Hunter's not here, but he was absolutely right. Like dissolves like. Good timing, Hunter. Like dissolves like. Polar solvents dissolve polar compounds and ionic compounds. Polar compounds are charged. Ionic compounds are charged. So polar solvents that are charged will dissolve both of those. Non-polar solvents dissolve non-polar compounds. Things that are not charged will dissolve other things that are not charged. So if we have water, a polar solvent, it's going to dissolve a polar compound sugar. Now sugar, sucrose, has completely charges all around the entire molecule. So what happens is that water will surround completely that sugar molecule to separate it from other sugar molecules to dissolve it. So that the water is completely surrounding that sugar molecule. When we're dealing with ionic compounds, the water, by its action, breaks that entire ionic compound. That ionic compound has cations and anions there. The water infiltrates it, breaks it apart, and then the water surrounds the ions. The positive hydrogen end of water is attracted to the negatively charged ion, the anion. The negative, the oxygen end of water, is attracted to the cation, the positively charged ion. Then you can have, if anybody has ever painted in their life, and if anybody has ever painted with oil paints, you know that in order to wash off from the oil paints, you either have to use something like gasoline or mineral spirits. Now, what happens when mineral spirits get around oil paints? The mineral spirit molecules will completely surround the thing that makes up the oil paint. And because it completely surrounds it, it will then dissolve it. Or better yet, a better example. Has anybody ever tried to clean up a greasy pan just with water and a scouring pad? Come on, have you ever?
Yes.
Yeah.
Is it easy?
No.
No.
That's because water is polar. What you're trying to do with that greasy, if you like fry up bacon in a pan and you try and clean up that pan with just water, there's nothing that's going to dissolve the grease. That's why you have to add soap, which has a non-polar content to it. So the soap that is non-polar kind of like mixes in with the grease and kind of like gets it mobile enough that it gets it away from the pan. Is this kind of like making sense to you?
Yes.
Nay, nay? Okay, so basically to know what like is, we gotta know what polarity is. And ultimately, you guys are gonna have a little bit more intense lesson when we get into Lewis structures and Vesper. But for right now, I need you to know what makes up a polar molecule. And polarity is a physical property of a molecule that involves the molecule having poles. In other words, the molecule has a positive end and a negative end. In order for a molecule to be polar, it needs to A, have a difference in electronegativity between the atoms that compose the molecule.
I have a question.
Yes, Hunter, go for it.
If a polar, okay, so like if an individual atom has poles, it's not just like how we think about like north and south. The electrons are swirling around it.
No,
right?
wait, time out, time out. Atoms don't have poles.
Wait,
Molecules.
molecules. I'm sorry.
No, that's
But
okay.
the molecules are composed of different atoms.
Yes, and the atoms that make up that molecule, if those atoms have the atoms that are bonded to one another, if they have an electronegativity difference, that means one of two things. If that electronegativity difference is great enough, then one of the atoms is going to grab the electrons from the other, and it's going to have the electrons. It's going to be negative. The other ion is going to be positive, right?
Okay. So that means that the introduction of extra energy, like let's say like heat, that would probably cause it to be like faster, right? Like a faster, like to solubilize faster, right?
I'll get into that later, Hunter. I don't want to talk about that right now. I will get into that in a few minutes. All right, so there are other times when that electronegativity isn't great enough for the one atom to totally grab all of the electrons from the other atom. What it does is it can grab it more times. They're sharing the electrons, but what happens is the electrons spend more time around one of the atoms than the other. If the electrons spend more time around one of the atoms than the other, then we have a polar bond. The other thing for the entire molecule to be polar, we have to have asymmetry. Let's look at water. Okay, if I was going to draw a water molecule, and you're going to be able to do this later, you're going to see later on that water is a bent molecule. Trust me on that for right now. It is a bent molecule. And the difference in electronegativities is big enough that the electrons want to spend more time around oxygen, but not enough that oxygen can totally grab those electrons. So I have a bent molecule, and I have a portion of that molecule which is negative and a portion which is positive. It's asymmetric. Therefore, this satisfies the qualifications for water being a polar molecule. Do I have questions on that? All right, we're going to shift to carbon dioxide. All right, carbon and oxygen have a electronegativity difference of oxygen being 3.4 and carbon 2.5. I have polar bonds. That electronegativity difference is great enough to make a polar bond. But the molecule is entirely linear. Think about if I had a 150-pound man on this side, and I had a 150-pound man on this side, and I had a rope between them. They're going to pretty much pull with the same force, right? So I'm literally pulling it directly opposite each other. When I do that, I make a totally symmetrical molecule, and therefore carbon dioxide is non-polar. Come on, guys. I know this may be confusing. Yell at me with something.
Where do we get the numbers for the electronegativity?
I looked them up in a chart, Jeff.
Oh, okay.
Basically, to be honest with you, I went back and looked up the slideshow I had from my lecture on periodic trends. That's where I found these particular numbers. Fair enough?
Yes, sir.
Can everybody see this? That this is symmetrical, so it's not going to be polar. Questions on it? Please yell them out at me. The harder one to understand is methane. First of all, I have carbon, which has an electronegativity of 2.5, and hydrogen, which is 2.1. In order to have a polar bond, I have to have at least a 0.3 difference. I have that, but I barely have it. So these bonds aren't very polar to begin with. But you have to understand, this molecule looks like these three hydrogens are like the bottom three corners of a pyramid, of a three-sided pyramid. And I got one hydrogen sticking straight up. That is perfectly symmetrical. So I have all of the forces equally and directly opposing the others. Because this molecule is entirely symmetrical, all the charges cancel out, and it is non-polar. Do I have questions on polar and non-polar? Anything, guys? Okay. Now we have saturated versus unsaturated. These are degrees to which a solution is concentrated. If we have saturated, the solvent cannot dissolve any more solute. Unsaturated, the solvent can dissolve more solute. I like to think of saturated as a Popeye solution. Anybody know what Popeye says right before he beats the snot out of Bluto? The exact quote is, "I can't takes no more." If you have a saturated solution, the solvent cannot dissolve any more solute. And unsaturated, yes, it can. So, what observation can you make to determine whether a solution is saturated or not?
The presence of solute in the solution. Like,
What do you
if-
mean by that, Jeff?
So like, let's say you put, like, I don't know what to use as an example, but like, let's say you have water and like a powdery substance. If there's still powdery substance left at the bottom, that would mean that it's saturated.
Exactly. If you look at a solution and you see solid there, you have a saturated solution. If you look at a solution and you don't see any solid at all, assume it's unsaturated. Yeah, I know there is that one super special instant where your solution is saturated, yet you're not seeing any solid. That's a very rare occurrence. What I want you to understand is that if you see solid in the solution, it is saturated. If you don't see any solid, then it is unsaturated. Now, Hunter, is there anything you can do to get more solute in the solvent?
For sure.
How?
You can raise the temperature.
If you raise the temperature, what happens is that makes the solvent more energetically active. So if it's more energetically active, it's kind of like going after this molecule and that one, and it's kind of surrounding all the molecules.
I have a question about that, actually.
Go ahead.
So I know that it makes it more energetic, but if, let's say, the solvent is full, or let's say it's fully saturated, if you add heat, what happens?
Well, if it's fully saturated, nothing.
Nothing will happen?
Nothing, because if it's fully saturated, well, let me ask you this question. By fully saturated, do you mean there is solid material on the bottom, Hunter?
Yes, like it's formed as much solid as it can.
Well, that's not, we're going the opposite direction.
Or sorry.
We're trying to get rid of the solid.
Okay, it's completely dissolved then. My bad. Yeah.
All right. If you have a saturated solution, you have solid on the bottom and you heat it up, well, what happens is this is a dynamic process. When I say that the solvent surrounds the individual molecules, it's not just surrounding it and staying there. It's surrounding it and then going off and going to another molecule to surround that one. So this is a constant process of the molecules surrounding one, and then one of the solvents goes to another solute, then it goes to another. This is a constant process. And if you heat up the molecules, that means it can go from one to the other. And the whole idea is we're trying to keep the solute away from the solute. Does that make sense, Hunter?
No, that absolutely makes sense.
Okay, now we can raise time. Is there something else we can do? And everybody here has done this. Is there anybody here that has not been told by their mother to make Kool-Aid? What is the second step in Kool-Aid, or the third step? You put the water in the pitcher, you add the Kool-Aid, then what do?
You stir it.
Oh yeah, you can stir it, yeah.
You stir it. And literally speaking, by stirring it, you are making the solvent more energetic and able to surround more of the solute. So those two things will make a solution dissolve more of the solute. So far we've been talking. When we're defining a solution, we have to define it by what makes it up. What chemicals? Salt in water, or salt water, sodium chloride in water. Napalm. We're going to put styrofoam in gasoline. Napalm. Both solutions. We have the chemicals. But also, we need to know the amount of solute in the solution or the concentration. So we need to know what makes up the solution and how concentrated it is. The two concentration terms we're going to use are mass percent and molarity. And guys, we've done mass percent. You've done it before. Mass percent is nothing more than the part divided by the whole times 100%. If we're dealing with solutions, the part is going to be the mass of the solute. The whole is going to be the mass of the solution. Any questions there, guys? The second term in concentration we need to deal with. Understand, there are going to be more concentration terms that you have to deal with. We're only dealing with two here. So, molarity is the second term, and molarity by definition, moles of solute divided by liters of solution. And note, guys, the label of the molarity is moles per liter. Write that down. That's going to be the label of what molarity is. Now, I'd like to take credit for this, but literally speaking, first semester I was teaching this, somebody came up to me and said, you know, Mr. Popovich, that molarity is just like density. You could just treat that just like you do a density triangle. And I looked at him and I said, you know something, you're brilliant. Because that's what you can do. If you have a molarity triangle, moles goes on top, liters and molarity go on the bottom. If you have the moles and the liters, it's separated by a line. If you divide the moles by the liters, you're going to get the molarity. Again, if you have the moles and the molarity, there's a line there. Divide the moles by the molarity, you're going to get the liters. On the other hand, if you have liters and you have molarity, you multiply liters by molarity, and you're going to get the moles. Questions, guys? Thank you, Jeff, for being my solid guide here.
Absolutely.
All right. Now, to do the solution to these problems, the problems that are due for this experiment, there are two ways to do it, and I'm going to show you both ways because he shows you both ways. I don't care which way you do it. Either way will work. What I need you to do is to understand one way and do it that way. You can convert mass percent to molarity. All right? Remember, mass percent. You're going to have the weight of the solute. You're going to have the weight of the solution. Divide the two, multiply by 100. You have the mass percent. All right. To do this conversion, assume that the percentage number is the grams of your solute. You divide the grams of your solute by the molecular mass to get moles. All right. Mass percent was grams of solute over grams of solution times 100. Well, if it's mass percent, then the grams of solute in the percentage is going to be divided by 100. So you're going to assume the grams of the solution is 100 grams. In these problems, you're also going to be given the density of the solution. To get the milliliters, you take the 100 grams that you assumed and you divide it by the density of the solution. That will give you milliliters of solution. Turn the milliliters into liters by multiplying the milliliters by 1 liter over 1,000. Last step, divide the moles of solute you got from step 2 by the liters of solution you got from step 3. That gives you the molarity. I don't like this as much as the next way. But that doesn't mean you can't do it this way if you understand it. A solution is 35.57% by mass lithium iodide. If the density of the solution is 1.20 grams per milliliter, what is the molarity? All right, I got 37.57. My first step says, I assume that my percentage is my grams. I have 35.57 grams of lithium iodide. I turn the solute into moles by dividing by the molecular mass. This gives me 0.2658 moles of lithium iodide. Because it's a percentage, I'm going to assume 100 grams solute. I divide it by the density of the solution. That gives me 83.3 milliliters times 1 liter over 1,000 milliliters, 0.0833 liters. Step 4, divide my moles by my liters. I end up with 3.19 molar solution, or 3.19 moles of LII per liters of solution. Questions on this? Other method. When we're going through this experiment, it's going to give you the mass of the solute. Make moles by dividing by the molecular mass. Second step, the experiment is going to give you the mass of the solution. Get milliliters by dividing. Dividing by the density. Then you're going to turn it into liters by multiplying by 1 over 1,000. Divide step 1 result by step 2, you get the molarity. If my evaporating dish weighed 70.186 grams and the mass of my evaporating dish and solution was 80.924 grams, and the mass of my evaporating dish and residue was 73.428. You have to understand the basic premise of this experiment. Basically, you have taken a solution, put it into an weighed the evaporating dish, and you put that solution into the evaporating dish, weighed it again. Then you have heated the water away. You've driven all the water off so that you have residue left. The residue that is left in my experiment is going to be calcium nitrate. I did the density of that solution and that was 1.14 grams per milliliter. So the mass of my solute is the mass of the residue. I take my 73.428, subtract out my 70.186, the mass of the dish. My solute weighs 3.242 grams. My mass of solution, 80.924. Mass of the solution in the dish minus the mass of the dish. This gives me my mass of my solution, 10.738. My mass percent, part divided by whole, 3.242 divided by 10.738 times 100. I've got a mass percent of 30.19%. If I'm doing the first method, I'm going to take that 30.19 grams of solute, turn that into moles, 0.1840 moles. I'm going to assume 100 grams of solution divided by the density. This gives me 87.7 milliliters or 0.0877 liters. I divide my moles by my liters. I get 2.10 molarity solution. Second method, I've got my moles by doing my subtraction. I've got my grams of my solute. I am going to turn my grams of solute into moles by dividing by the molecular weight. 3.242 grams makes 0.01976 moles of solute. I also have my mass of my solution. I'm going to take my mass of solution and divide it by the density. 10.738 divided by my density equals 9.42 milliliters times 1 over 1,000 gives me 0.00942 liters. I divide my moles of solute by my liters of solution. I also come up with 2.10 molar solution. Again, whichever way makes sense to you, use that method. Questions, guys?
I'll probably go with method 2.
I think it makes more sense, but that's me. Okay, I am going to get into here. Is everybody seeing the screen I have up there now?
I can.
Yes.
Yes.
Okay. I'm getting into the course content where I'm going to go and take you through the results section. Really and truly, there's not a lot to this laboratory. You're going to need to look at the results from part C. And what it is a series of pictures. What you're told to do for part C is you're told to put 1 gram of sodium chloride in 5 milliliters of water and in a separate test tube, 1 gram of ammonium chloride in 5 milliliters of water. And you're supposed to determine whether this is saturated or not. Then at room temperature, you're going to add another 1.4 grams of sodium chloride to the solution with 1 gram and 5 milliliters. So you have a total of 2.4 grams of sodium chloride and 5 milliliters at room temperature. Same thing with the ammonium chloride. Determine whether those are saturated. Next, you are going to heat it. This is the 2.4 in 5 milliliters after heating, then after it's allowed to cool. This is the 2.4 of ammonium chloride in 5 milliliters after heating. Then what happens? They let it cool. The solid comes back. Questions about part C? All right. Yes. Huh. All right. Now we're going to get into the results section as it is. Okay. You're going to be given those three amounts in the report. I'm sorry, in the handout, the laboratory handout. It's going to give you weight of the evaporating dish, and solution, and weight of evaporating dish and residue. The residue is either going to be KCl or NaCl. You have two of these problems you're going to have to work out. You have to figure out from that information what the mass of your KCl solution is, what the mass of your residue is, how much water got evaporated. If you have your residue and you have your solution, you subtract the two of them, you get the mass of the water. Then you have the mass of the solute, which is the residue, and you have the mass of the solution. Determine the mass percent of KCl. All right. Now you have the weight of your solution. You are going to divide it by the density. That will give you the milliliters of your solution. You have the weight of the residue, which in the first example is your KCl. You're going to multiply the weight of your residue by 1 mole over the molecular weight, and that will give you the moles of KCl. Then you divide the moles of KCl by the liters of solution, you get the molarity. Does he have nothing better to do at this time than make up choices like this?
I'm saying, man, this guy.
All right, that was part A. Part B, you're going to do the same exact
Hey,
calculations.
Sophia, mute your mic.
Buffy.
Who's not
He
muted?
does look like his dad.
What? Wait,
Guys,
who?
somebody's
Grace.
somebody's watching TV, which I don't necessarily mind, except it's distracting those.
Yeah, I heard something about Zelda. Now I'm interested.
Hunter, You get distracted easily.
Yeah, I know it's bad. All right, let's get back to it.
The part B, you're just going to be given another 3 sets of numbers. Mass of the evaporating dish with solution, evaporating dish with residue. You're going to do the same calculations that you just did. Now, part C. All right, you're going to look at those pictures I just showed you. And you're going to look at the 1 gram salt for 5 milliliters, and you're going to determine which ones are unsaturated or you're going to determine whether each one is unsaturated or saturated. Then you're going to go look at the 2.4 per 5 milliliters at room temperature. Determine whether they're unsaturated or saturated. Then you're going to do the same thing at the elevated temperature. Again, just looking at those pictures of the part C. Then which salt solutions became saturated when they were cooled. And last thing, how do you know if it's saturated or not? Post-lab questions. This one just mimics a mass percent. The 14.5 grams is the solute. This is just the weight of the solvent. Be careful. Okay, you've got a weight and a molecular weight. You can get moles. You've got that much solution. Assume that that solution is the weight of the water is, or the volume of the water is the volume of your solution. Another mass percent problem. You've got the total weight. You've got the weight of the residue. Anybody have any questions? That's all I got for you guys.
I just have a quick question.
Faith,
wait, never mind.
go ahead. Go ahead, Faith.
I was gonna ask if we could like double check our answers with you, but if we just look at the lab, we don't really have to type anything in, do we?
No, nope. This is going to be multiple choice. So if you don't get an answer that matches, then you probably did something wrong, Faith.
Yeah. All right, thank you.
Anybody have anything else? Okay, Hunter, Faith, Victoria, and Jennifer. Is there anybody else that I have in lecture? I would like to just get the four of you at least. Anybody that has me in lecture, stay afterwards for a brief moment.
Okay.
Okay.
Take care, everybody else, unless you have questions. If you do, I'm here.
Thank you, sir.
Take care.
You as well.
Thanks. Take care.
Have a good night.
Good night. Bye, Grace. You don't have me for lecture, do you?
No, I don't.
Okay. If you don't, do you have any questions?
No.
All right, I will see you then. Maverick.
I was hoping to see, is he asleep?
I
Or
don't know.
yo, Maverick.
I'm not seeing his whole head, so I don't know. Sophia, do you need anything from me?
Maverick.
Sophia?
No, she's KIA. Or
I think so too.
sorry, MIA.
Okay, Maverick,
Hey,
log
Maverick.
out, log out. Log out, Maverick, okay?
Love
We're
you, man.
done.
99, man.
Go view
Awesome.
the video.
Listen, he was here the whole time.
I was.
Yeah, I know he was here.
No, I'm saying I literally saw it. Like it was
I'm
like
kidding.
the last 2 minutes, all right?
I'm kidding, Hunter. Maverick, I'm kidding. Okay, Maverick, we're done.
All right.
All right.
All right.
Good evening, everyone.
For you four, I'm very, very sorry if you had any problem getting into the test. I'm sorry about that. It's something I overlooked. I needed to put it into course content. I did not. That's on me. So I apologize for that. Hunter said it was already the toughest exam he's ever had.
Yeah, that wasn't fun.
I
Honestly, for me,
I
it was
knew it
mainly-
wasn't going to be. Jennifer?
Sorry, no, honestly, for me, it was just that ammonia question.
Yeah, that ammonia question really screwed me up.
Like I said, I took a knee on that one.
I think if you watched the video of when I was recorded, I think I dropped the F-bomb a few times because I was just like, I don't effing know. I'm like, I really don't effing know how to do this.
Okay.
Same, I literally looked at it.
By the way, did you guys see my, I don't know if you can see this or not. Did you
I
see
saw it
my
at the beginning.
Easter present?
That's cool.
That's so cool.
Don't give
All
it to
right.
your dog.
All right, easy enough. That was probably the easiest problem on the test.
That was the hardest
Wait, what
problem.
are you talking about?
Like empirical formulas, so like all
The
that.
easiest was-
Fine.
The easiest was number 1.
Yeah.
It's
With
All
the
of it was
log.
hard. Nothing was easy except for the percent compositions.
Yeah, that
trust
wasn't.
me.
That was
Trust me.
rough.
I hope you guys wrote a lot because the more you wrote, probably the better chance you have of.
I wasn't sure about the log question though, because it's like you could just put that in the calculator and get your answer. So I didn't know.
Exactly.
That was the
Literally,
point.
exactly. But you gotta
Basically, you just
remember,
had to
it's,
write it out.
it's negative log.
Listen, as someone who was an English major, I overwrite everything, and I was like, do I write a whole essay about why this is what it is?
Oh, there it is. Good.
That's what I
God.
kind of did.
I explained like every step I was going.
All right.
I was overthinking. I hate it.
Dear God,
Should
I
I
hate
get a-
this.
I'm so hungry.
All right, 1 second. I need to
I'm
get
making
in
chicken
here.
soup.
By the way, I learned about heat being able to solubilize things because as a bar back in bartending, I make simple syrup. It just makes drinks more sweet. So you get boiling water and you just throw the sugar in there and it dissolves like that. You know what I mean?
Okay, we got our formula here, right?
Yeah.
Basically, I said something like you had 3217 grams of NH3, right?
It was mine was
No.
something like that E20 or E3.
Oh,
It was like
that's easy.
3 point.
Are you talking about number 7?
Yeah, that's the
E3.
same. That's the same thing. You just move the decimal.
Oh,
point.
okay.
Yeah.
All right, so I got 3217 grams of NH3. Question is, what is the mass percent of N2?
Oh
So
my
I have
God.
I have a quick question before you continue. So the question reads, if so and so grams of nitrogen was produced, not NH3.
Yeah.
So maybe I think that's where we all got confused because it was asking if 3.765 whatever grams of nitrogen was produced, what is a mass percent of nitrogen in the final mixture? So it didn't say what that was the amount
I don't
of
care.
ammonia.
I don't
I'm
care.
just saying that's what threw me off. So I didn't know how to.
Yeah.
All right. First of all,
Mhm,
looking at the equation,
mhm.
I started with NH3, right?
Mhm.
Did I lose any of my nitrogen or any of my hydrogen by conservation of mass?
No.
No.
Well, no.
So literally speaking, if I started with my nitrogen. Ah, crap. All you have to do, that's the simple way. If you started
Jeez.
off with nitrogen, if you started off with a compound that had a certain mass percent of nitrogen, you're going to end up with that same amount of nitrogen.
I'm so mad at myself. I literally had that written down. I was like, no, that can't be it. And then I erased it.
All right. That was the easy way to do it.
I think I got close. I got like 82.23% or something like that. It was close to it.
The other way, the hard way to do it, if you have 3217 grams of N2, turn that into moles. 1 mole divided by 28.02. This gives you 114.8 moles of N2, 114.8 moles N2 times 3 moles H2 divided by 1 mole N2. This gives you 344.4 moles H2, 344.4 moles times 2.016 grams per mole equals 688.8. Final answer, you've got 3217 divided by 3217 plus 688.8. So even if you didn't want to go with the conservation of mass, it wasn't that hard a problem.
I think I got close to the first percentage because I was like,
Well,
I was like, it's 82. I think it was like 82.22 I got or something like that. I was like, you know what? It's a percent good enough. I'm out.
oh crap, somebody remember 3906?
Okay.
And that's only due to rounding errors. So we'll see, Victoria.
Yeah, that test I don't want to keep second guessing myself, but that was pretty rough. I came in like confident knowing how to do all the steps. And then I took the exam and I'm like, I don't know. I'm just
All
a
right.
bad test taker.
Everybody
It
says
was
that.
like running up to Goliath or something.
Hey, I warned you guys before this test, before we started this, that this was going to be the hardest section.
I mean, I did practice problems. I did all of it and it's still like it still tripped me up a little bit, but I tried.
Yeah,
Okay.
honestly, I think the rest of the test for me was fine. It was just
Yeah.
a problem. I didn't know where to start. I think it just confused me.
Where am I? Quizzes. Yeah, and that's not what I want to be. Well, it is, but it isn't.
It is.
Okay. Leandre is just getting in. Leandre, he may have, to be fair, he may have just finished the test.
Yeah.
Yeah.
Leandre,
Okay, so that's how you do.
Yes.
you're gonna have to look at the video for this one.
Okay.
I take it you just got done with the test or something?
Yes.
Yes, it was hard. We're all
Yeah.
Well, everybody except one person is commiserating about this. I give you the idea of Leandre, who the one person that's not commiserating is.
Is it you?
Yeah, exactly.
You know what? That's a great word.
Commiserating.
Good
Yeah.
$5 word. Yeah.
Yeah, that's a Blink 182 or whatever.
Okay, I'm gonna take my viewpoint through these, okay?
Okay.
Add edit questions. Continue. Bottom line, first question. Piece of cake.
Yeah, that wasn't.
Piece of cake. All you got to do, take the log of that number, punch in log, type in that. You're going to get a negative number, make that negative number positive. You're done.
It was like 2.24 or something like that. I don't remember. Yeah.
Second question. Again, not that hard.
Yeah.
Turn the milliliters to liters, multiply it by the molarity. You get moles. Potassium nitrate, KNO3. You can get the molecular weight. You divide you multiply the moles by the molecular weight, you get the grams.
I think number 4 threw me off because I got like an insane number for that.
Then you probably did a calculation wrong, Victoria.
I got like, because I never know if it's close enough to.
I think what the result, what it came back to was it came back to 1 carbon to 1.3
Yeah, I did like.
hydrogen to 1 oxygen.
I rounded because I never know if I should round. I think it was like 1.38 or 1.39, and I rounded it to 1.4, and then I times it to get it out of that. It just like, I feel like I ended up with an insane number at the end.
Well, if you did that, Victoria, then you're going to get a lot of points for it.
Okay.
This question. Third question. Where are you at? Thank you. Third question should have been fairly easy for you as well. Yeah, it's all, in retrospect, it's all easy, isn't it?
Yeah, when you're not, pressured by a clock.
Yeah.
Or me having to drag my computer to go plug it in because it had 25% left.
Okay, damn it, I didn't want to do that. Percent composition of each element. You have iron, oxygen, and hydrogen. All you're doing is taking the atomic mass of iron, dividing it by the molecular weight. Taking 3 oxygens, dividing that by the molecular weight, 3 hydrogens, dividing by the molecular weight.
That one was good.
Now, this one, I tried to make you understand that this was S8. So therefore, to get the molecular weight of the sulfur, you had to multiply 8 times 32.06. Straight. This is a straight limiting reagent problem.
Did we, I put it in there anyway. Did we have to tell you which one was the limiting reagent?
I don't recall I don't think I said it.
Okay.
I did just for my own.
Yeah.
I was writing it out so that I can remember. Okay, this is what it is. Now let's go to this part.
Yeah, I did too.
Back to exam 3.
Yeah, my answers are long because I literally wrote out each step. I was like, okay, let's start with this, do that. Next, I wrote find this. Then I wrote.
Yeah, I did the same thing. I'm like, am I writing a dissertation on this or something?
As if I was writing it out on my.
I might have neglected to put a couple of the like labels and stuff, but I
We'll
wrote
work it out. Hunter, I'll try and see what you're doing. If I can make sense of it, you'll get credit for it.
okay.
All right, we have grams of iron and we have rust that weighs 108.2.
Wait, whose water broke?
This sounds like that's obviously more important. So how do we get the oxygen, guys?
You subtract the iron from the total mass of the rust.
All right, once you get the iron, turn that into moles of iron, get the grams of oxygen, turn that into moles of oxygen, whichever one's smaller, and it turned out to be, the ratio of that was 1 to 1.5. Do we have water breaking, Andrew?
Oh yeah, it's. I thought it was my cousins or whatever, but it's my mom's friend or whatever.
Okay, it's not the phosphate thing.
No.
Something more important than the phosphate thing.
No, I thought it was my cousins because then I would have to contact them or whatever.
Okay, guys, this problem. Can I use MAVA equal MBV?
Yes.
MAVA equals MBVB. Can I do that here?
I did. Oh God, was that wrong?
It's wrong.
Yeah, I did that too.
All right, how many OHs?
One.
How
No,
many
3.
H's? No,
Ah,
how many
damn it.
OHs?
Wait, OH is 1, yeah.
And H's?
3.
So
Ah,
they're
shit.
not the same. So you cannot do MAVA equal MBVB. You have to take the milliliters, turn it into liters, multiply it by the molarity of the KOH to give you moles of KOH. Then you have to multiply the moles of KOH by 1 mole of H3PO4 for 3 moles of KOH to get the moles of H3PO4. Then you divide it by the liters of H3PO4.
That's right, because with acid-base formulas, you have to actually look at it to see if it's, oh yeah, that's what I overlooked that. That's okay. Okay.
And the last problem, straight, this is a straight stoichiometry problem.
Thank God.
Multiply liters, turn this into liters, multiply it by that. It turns out to be 0.06, I believe. Then you multiply this by 1/3. So that gives you 0.02 moles of this. And you multiply this by the molecular weight, which God knows what it is at this point.
All right. That was big, actually.
Yeah.
Or like 800 something, I think.
Yeah, it was a big number.
Yeah.
Yeah, it's like 811.
I think you're right. I think you're right, Hunter.
Yeah, I think if you watch my video, I was like, whoa, that's big. I was just like, that's a lot.
I have a very good feeling that I did not do well on this at all.
Yeah, I
You
agree.
might be surprised. Let me wait.
Ooh.
Just wait and let the things fall out, and we'll see where we're going from there. Okay.
I don't.
Extra credit.
Yeah, I don't mind writing things out because it's like you at least get partial credit for showing your work versus just getting it completely, like doing all the work and then getting it completely, like even the answer is wrong, but at least you have your work. So it's like a double-edged sword here. I don't know.
It's a pain in the ass. I know it's a pain in the ass to do it here, but believe me.
Yeah.
Can I volunteer at a chemistry lab for some extra credit?
I'm sorry. I've seen your work in the exam. No. I'm sorry, but that was too easy.
I'll do a damn charity drive for the nearest
Damn.
nuclear plant.
Guys, don't panic. Wait till the scores come out. Then
Mhm.
we'll see where we're going from there. Okay.
And then we'll panic.
Okay.
Okay.
Yeah, I don't want
It's
this
not- I mean,
test to
I'm s-
dictate like how much I know, because it's like I feel like on the practice problems and everything I did well, and then I hit this test and I'm like, what the hell? It's kind of what happened.
It's no, that is part of the problem of this exam. Okay.
Yeah.
In retrospect, what I probably should have done was I probably should have eliminated that extra review for the last test and did empirical formulas on that test in retrospect. But I had things on my mind that were other than dealing with that at that point.
Mhm.
Trust me. All I can tell you guys is trust me, okay?
Okay.
I'm not going to screw you. Take care, guys. I will see you on
Thursday.
Thursday. We're starting gas
Yes.
loss on Thursdays.
Okay.
Done. Thank you, Professor.
You do have
Thank
a quiz. You do have a quiz,
Thank
dude.
you.
Yeah.
Take care.
Yep.
15, yeah.
Take care.
Thank you.
Thank you.
All right. I'll see you.
Bye.
Bye.
Gonna go watch some what was that one joke you made that was so funny with the Flintstones swingers? That was hilarious. That was the funniest one, man.
Hunter, I get compliments on that all the time. And you know something? When administration finally sees that somewhere, I may get my ass fired.
Nah, yeah, right. Whatever. No, it's a good analysis, to be honest.
But to be honest with you, I have a lot of people that know what that means afterwards.
Yeah. All right, I'll leave you alone, all right?
Take care, Hunter.
All right, I'll see you on Thursday. Bye.
All right, bye.